It's already 10. I think we should begin now. So, morning, everyone. I think we're still waiting for a few to join, but let's just go ahead. Okay. So, this class, we're going to learn about a new particle removal device. So, just recall what we have gone through. All right. So, we have learned two devices, right? The first one is gravitational settler. We realize that the efficiency for the gravitational settler or the settling chamber is quite low, right? It's just using the gravity. It's a passive method to remove particles, and it happens when we transport the flue gas from the combustor to the stack, right? And then we learned about cyclones, which is a little bit more efficient. In terms of mass removal efficiency, it can be around 90%, right? Mainly because the mass is dominated by larger particles. And then the cyclones have a higher efficiency for larger particles, let's say above 10 microns. And this class, we're going to learn a new device, which is called the electrostatic precipitator. People also call it as the ESP. So I'm showing the name here. So before we introduce new contents, let's still do a recap, right, of our last class. So last class, we basically learned how we can do the calculations for cyclones, right? We went through an example, which the problem gave us a size distribution of the particles in the flue gas. It gave us the dimension, right, of the cyclone, working condition of the cyclone, and wants us to calculate what is the overall efficiency of the particles. So basically what we need to do is we need to first calculate what is this cutoff size. So you see this cutoff size is dependent on the viscosity, which is a function of temperature, right? The working condition, the width of the inlet, right? The number of effective turns of the gas in the flue gas, right? Inlet velocity, particle density, and gas density. That's all. We plug in these numbers, calculate the cutoff size, which should be typically in the scale of micrometers. Okay, so if you get something that's in nanometer or get something that's in meters, I think that's wrong. Okay, so the same applies for a project, right? So try to get some number that's reasonable for the ESP. So once we get this DPC, we can calculate the efficiency for particles with all different sizes, because finally the efficiency is calculated by this equation, right? 1 divided by 1 plus DPC divided by dpj. So dpj is the size that we're interested in. For example, if we're talking about this size distribution, then we can first derive, or we can first find out what is dpj. So that is just the average of the size range. It's going to be 1, 3, 5, so on, right? And with the dpj, we can calculate what is eta j, okay, using this equation. So we have mj, which is the percent of the mass in each size bin. And then we can calculate eta j multiplied by mj, right? It's going to be the removed mass in each size bin. So finally, when we calculate the overall efficiency, that's going to be either the summation of eta j mj divided by the summation of mj. Okay, so this is how we calculate the overall efficiency. You'll get more practice in your homework problem that's due next Monday. So at the end of last class, we also mentioned about the electrostatic force, because to remove the particle with the electrostatic precipitator, we need to use the electrostatic force. And we use the electronic book or the Kindle as a simple example there, right? We saw that people use these electrostatic force to control or manipulate the movement of the particles under the electric field. So we also demonstrated that under the reasonable condition of a Kindle, let's say an electronic ink device, the response of the ink for refreshing a page, let's say flipping the page, is quite slow, right? It takes around 0.25 seconds. So that's why that's why maybe some people like that feeling, right? It feels like reading a book, flipping the page needs some time, but definitely not for me, right? I don't like that response there. So, but for Kindle or for those ebooks, there are for sure advantages when we read them, right? It doesn't harm our eyes compared to the other electronic devices. It doesn't have the background light. So we have to read it under natural light, right? Under lamp or under the sun, right? Without the external or background light, we can't read the text on there. So it's a little bit healthier to our eyes, right? So that's all for the contents of last class. So this class, we're going to learn about the ESP. But one thing we didn't mention for the ebook or the Kindle is that we assume that all the particles are already charged. But how do we charge the particles? Because actually most of the particles are neutral in our environment. So here I'm showing a graph that's showing basically the fraction of particles carrying different charges. So it's showing here. Under natural condition, what you can find out is that, let's say for particles below 10 nanometer, so this is showing nanometer, which is 1,000th of a micrometer. So for particles below 10 nanometer, you can see that the fraction of particles with zero charges, which means that they're neutral, is almost 100%. Okay, so this is 1, right? Which is 100%. So all of them, almost all of them are neutral, doesn't have any charge, right? And then it's only maybe, let's say, particles reach to around 100 nanometer where you start to have, let's say, 40%, 40 to 50% of them being neutral, and rest of them being charged, right? As the particles size become larger, let's say 1 micrometer, more and more of them are carrying charges. Fewer of them are neutral, basically. So this is under natural condition, and you may wonder, I mean, most of the objects in our daily life should be neutral, right? So where are these charges coming from? Right? Where are these +1, -1, +2, or -2 come from? So it can come from a lot of sources. Although in our natural condition, we don't use the high voltage to charge the gas or charge the particles. There are a series process that give them charges. So for example, there's photoionization. So what happens is that the solar radiation contains a lot of UV light. We mentioned in our first class about the ozone being able to block the UV radiation. Right? The UV radiation is a strong magnetic wave there. It has a high energy. So with the high energy, it can knock out the electrons from a lot of gas molecules. For example, oxygen, nitrogen, right? And forming oxygen plus, nitrogen plus. And then, of course, you get oxygens outside, right? So basically, you can form these positive or negative gaseous ions, although they're not particles yet, right? But they can move around and collide with the particles that's in our atmosphere, right? So they can bombard the particles, and therefore you can give them charges, right? So there's also radioactive ionization. We know that probably in physics you learned about alpha radiation, beta radiation, gamma radiation, right? So when you have radioactive materials, they're going to self-decay. For example, the alpha radiation, let's say the alpha radiation generates an helium ion, right? It has a mass of a helium, but it doesn't have any electrons on that, right? So this is a charged gas molecule. So similar to these gas molecules or ions, they can collide with the particles. So beta radiation just directly give you electrons, so they can collide with the particles, make them negatively charged. So gamma radiation doesn't give you any charges, but a lot of the radioactive materials, for example, radon. So we know that almost everywhere there's radon molecules, right? So especially in the underground, situation. Let's say during mining, there are a lot of radiation being emitted, and radiation is a basically can emit alpha radiation, right? So these alpha radiation are charged gas species, so they can collide with the particles, right? So that's why people say that it's hazardous to inhale these charged particles from the radioactive materials, right? So they can emit a lot of these ionized species, right? So under the natural condition, because of the photoionization and radioactive ionization, we can get particles charged with different charging states. They can be +1, -1, +2, -2. Right? As particle size become further larger, you can even have particles charged with three charges or more. Okay. And another interesting thing you can see from this graph is that even for particles with the same number of charges, let's say for particles with 100 nanometer, okay, you see that there's a higher fraction of particle carrying -1 charge than a fraction of particles carrying positive charge. Same for the -2, there is a higher fraction of particles carrying -2 than +2. Okay, so the reason behind that is because of the molecules or because of the ionized species that's giving these charges. So for example, what type of species are giving these particles -2 charge? It's electrons, right? So electrons are very small. They can move around very quickly, diffuse much faster compared to these positive ions, right? So that's why typically we can see a higher fraction of particles carrying negative charge than the positive charge, right? So basically this is the charge fraction of particles under the natural condition. And one thing we can notice is that the charge is not high enough, right? The charged fraction is not high enough. For particles below 100 nanometer, we can't really charge a lot of them under the natural condition. So therefore, we have to use some other methods to give these particle charges so that we can manipulate their movement and further remove them. So what are these other methods, right? So we can use triboelectric charging. So triboelectric charging is just a friction. So if you use a piece of silk and a piece of cotton, I think people are also using this method to make their homemade masks, right? So if you have some materials, fabric materials, and then just move them against each other, you can generate these charges coming from the friction. And we call these as the triboelectric charging. So once we make that, if you make this material as a mask, you can further repel the particles with the charging. Although we don't know how long the charge can retain, typically they can dissipate pretty fast. But this is one way to generate charge. But it's quite unrealistic to charge the particles, right? So if we can already put particles onto a surface, then basically they're already precipitated. There's no need to remove them from the gas stream. But we're talking about the removing particles in the gas stream or the aerosols in the gas stream, right? So we can also use conduction. Conduction just means that one object is charged, and then when it collides with the other object, you can transfer the charge onto the other object, right? But this is also for the larger objects, but for smaller particles, it is difficult to do this charging, okay? So the final or the last method we're talking about is called the corona discharge. So what corona discharge means is that we can use a very thin needle, okay? And then we can connect them onto a high voltage, okay? So the other side can be either a needle or a flat surface, okay? Or it can be a flat surface. So these can get connected to the ground, okay? So what happens is that because of that thin needle at the tip of it, it's going to generate a very strong electric field. So because of this electric field, when oxygen or nitrogen, these gas molecules pass by, this strong electric field, let's say it's connected to the positive high voltage, is going to grab the the electrons from the gas molecules. So basically the electrons will get collected onto the needle, and then what we can generate is just oxygen, positive charged oxygen molecules, or oxygen ions or nitrogen ions. Okay, so this is a way to ionize the gas molecules. And then if we further introduce particles into this gap, then these ions can collide with the particles and give them positive charges, right? So this is another way to generate the, to give particles charges. And actually there's an advantage for the coronal discharge, mainly because if you see the polarity of the molecules or of the ions, so almost all of them will be positively charged, right? Mainly because all the negative charged ions, they're already collected onto the needle. And then because of the electric field, because of the repulsion among these molecules and also the repulsion of the needle, so the particles can get deposited while they are being transported through this gap here. Okay, so that's why in industry, we use this coronal discharge a lot to charge the particles and then further put them under an electric field to collect these particles. So we mentioned that these two are not realistic for industrial applications. So actually, it's same for these two methods as well. So photoionization will involve UV light. I don't think it's safe enough to use these high energy light or to let people to operate these, right? It's quite dangerous, high energy radiation there. So radioactive material, the same. Right? We don't want to operate these materials or dangerous materials. So that's why coronal discharge is the most widely used method to charge the particles and to remove the particles. Okay, and the coronal discharge is being used in the application of the electrostatic precipitator. So here, what I'm going to show is a very short video about the coronal discharge. So you probably have already seen that from very simple experiment. Not sure if I shared the sounds. Share computer sound. Okay. So you see here we have an alligator clip, right? So this is connected to the ground, right? And then we can also bring a needle close to the tip. So when they're getting very close, you're forming a direct current, right? Mainly because you ionize the air in there, right? Because of the ion concentration is so high, they can form a current, which looks very bright in there. But when you put them apart, you see? So this is called the corona, okay? It doesn't look very bright here because you're not forming a direct current, but these blue colored things here are basically the ionized gas molecules, okay? So the reason why they're showing blue color is also because the high voltage gave them a high energy there, and because of the energy hopping, so they have to release the energy from the high energy state, and there is a limited the band gap that's describing this and release amount of energy, and that band gap corresponds to the fluorescence wavelengths of the blue light. Okay, so this is going to form like a cloud of ions here. This is the coronal discharge. And of course, when you get closer, it's like lightning, right? So you're forming this direct current again. But in industry, we want to form this coronal discharge. We want to form the ionized gas molecules. We want the blue things here. We don't want it to form these direct current. This is the state when we're trying to form the coronal discharge. Okay. So if you have a high voltage power supply, you can probably also try that at home. Right? So this is a coronal discharging, and now it's the ESP. Okay. So the ESP, the full name of it is Electrostatic Precipitator. Okay. So this is a very simple schematic diagram of an ESP. So what happens is that flue gas, which is the particle, which is the gas flow that has a lot of particles in there, polluted species, right, will enter from here. And then inside the ESP, you can see a lot of parallel plates. So these parallel plates are also called the collecting plates. So they are connected to the ground, okay? And then you can also see these vertical wires hanging here, okay? So these vertical wires are basically the discharge electrodes. That's a thin needle we talked about, right? So the discharge electrodes are going to get connected to high voltage. So because of the thin wire there, they're going to ionize the gas molecules flowing by. And then the particles will also get charged. And due to the electric field that's built on the ESP, then the particles can get collected onto the ESP, right? And you see here are also some wrappers. So the wrappers, the use for that is basically generate the vibration. So after some time of operation, you can vibrate the plates here. So once you vibrate it, then the collected particles can just fall down onto the finally the collector here. Okay. And typically for ESP, it's composed of multiple compartments. So for example, for this ESP here, it's composed of let's say 1, 2, and 3 compartments. Okay, so each compartment will have a group of these parallel plates. And this compartment here, so each compartment is called a mechanical field. Okay, so for example, this one contains 3 mechanical fields. Okay, so each mechanical field is composed of an array of these collecting plates, an array of these or a matrix of these corner wires, right? And then basically the particles will go through the ESP, right? Well, composed of multiple mechanical fields, and then get collected onto the collecting plate. And the flue gas out is the remaining particles, or the remaining flue gas that's cleaned with the particles. So the ESP is quite efficient. It can remove larger than 99% of the particles in terms of its mass concentration. Again, we're talking about mass concentration. So recall for the cyclones is around 90%, right? It's already quite efficient for large particles, but the ESP is more efficient. The ESP also have the problem of basically a lower collection efficiency of very small particles, but compared to the cyclones, they're efficient enough. Okay. So here I also have a short video about the ESP.
A precipitator operates.
Okay.
A precipitator operates in an enclosed chamber. Inside the chamber are collection plates that are connected to the grounded outer frame. Positioned around the collection plates are discharge electrodes. The electrodes are negatively charged with high voltages and are insulated from ground. As flue gas flows through the chamber, dust particles and other entrained flue gas components pass through the high-energy field and become ionized. This drives negatively charged ions and particles to the collection plates. The particulate matter builds up on the collection plates and forms a layer.
So this is a very short video about the function of the ESP. So one thing that we forgot to mention is here. Let's go through that video again.
Positioned around the collection plates are discharge electrodes. The electrodes are negatively charged with high voltage.
These electrodes are negatively charged. So the reason why it's negatively charged is because when you ionize the air, it's going to attract the positive ions to the needle, right? So those are oxygen positive ions, nitrogen positive ions. but the ions to charge the particles are going to be electrons. So electrons have a higher mobility, can charge the particles more efficiently. So that's why we have to use, typically people will use the negative high voltage as the electrode for the corona needles, right? So basically we can generate more mobile charged species to achieve a higher collection efficiency. Okay. So so if we go back to the geometry of the ESP, so we mentioned that it's composed of mechanical fields, right? And then each mechanical field is composed of basically a few numbers of parallel plates. So let's assume that there are n numbers of the parallel plates in this compartment. Okay, so what we can see is that the charged particles are going to get collected onto the basically onto the side of the plates, onto the surface of the plate, right? So let's say for the plate that's in the middle, so it's going to have two sides, and both of the sides are going to collect particles, right? So in terms of total size, in terms of the total area of the ESP, of the collecting plates in this mechanical field, that's going to be 2n here, okay? But how many plates are actually collecting the particles? So let's do a quick quiz here. This is a very simple problem here. Okay, so there are, in each mechanical field, there are n number of plates, meaning that there are 2n sides. So how many sides are collecting particles? Okay, 5 more seconds. Okay, we'll stop here. All right, so it seems that we have a tie here. It's going to be either option 2 or option 3. All right, it's not the first option. It's not the first one, because as we mentioned, for the plates that's in the middle, both sides of them are collecting particles, right? The corona wire on the left and corona wire on the right are going to charge the particles, right? So particles can get collected on both sides. So it's going to be something like a 2n in the final term, right? But based on the geometry of the ESP, you see that there's no wire further outside this external plate, right? So the plate sets at the ends of the mechanical field, they only use one side to collect particles, right? And because of that, the size, or the number of sides that's being used to collect particles are going to be 2n minus 2, mainly because we just have two plates that's at the ends that we don't use the surface area, right? So because of that, we need to choose the third option, which means that 2n minus 2 sides are being used to collect the particles, okay? So just to make sure that you understand this problem, let's just relaunch the pooling. Let's see if you get the correct answer. Okay, 5 more seconds. All right, so Yeah, I think we can just go ahead, right? So there's one person that still don't quite understand this, but if you have any questions, let us know, okay? It's going to be 2n minus 2. So this is a quite important concept when we design our final ESP, because finally the efficiency of the ESP is dependent on the total area of the total area of the plates being used to collect the particles. Okay, so let's say if we calculated that the required area is 100 square meters, right? And then we have to consider the area that's not being used to collect the particles. So the actual area have to be larger than 100 square meters. So it's going to be either 110 or 150, but we have to consider the extra surface that's not collecting the particles. Okay. All right, so let's go ahead. And so there are some advantages and disadvantages of the ESP. So the direct advantage is that we mentioned the ESP is much more efficient compared to the cyclones, right? So the ESPs are very efficient, right? Even for very small particles, they can charge the particles and collect them. So they can handle very large gas volumes with low pressure drops. Compared to the cyclone, notice that we don't have to push a very high flow speed through the ESP, right? It can be just a large amount of flow rate, but with moderate flow speed. So it doesn't create a large pressure drop, which means that the maintaining or to operate the gas flow, it doesn't cost a lot of money. And so it can conduct the dry collection of valuable materials or wet collection of fume and mists. Okay, it doesn't matter whether it's dry or wet. It can be designed for a wide range of gas temperatures. Really, the gas temperature doesn't affect anything here, right? Low operating cost, except at very high efficiencies. So typically, the higher efficiency we want, people will use higher current discharge voltages. So just to think about, basically, we want to charge more particles, right? If we want to charge more particles, we need to create a higher concentration of the ions from the current discharge. So what that means is that we have to put in a higher voltage to the electrodes. So that will cause higher costs. So it can handle heavy dust loads and also durable, has a long service life, right? We don't have to replace it for a very long time. So it also has some disadvantages. So the most important one is the high capital cost. It means that to build that, to construct this device, we need a lot of money to do that, right? Because the internal structure is much more complicated compared to the cyclone. Cyclone is just, I would say, it's just a metal cylinder, right? But the ESP is composed of so many plates, and you also need to choose very thin metal wires to generate the current ions. So it will not control the gaseous emissions. This is same for the cyclones. Not very flexible, so once it's installed, it's quite difficult to change the operating conditions, because let's say once we fix the flow rate, once we fix the high voltage, it's going to be quite difficult to change the device. Otherwise, the collection efficiency will be different. It also takes a lot of space compared to the cyclones. So it might not work for particles with high electrical resistivity. So what this resistivity means is how easily it can get charged, right? So for some of the materials, they're just basically not conductive. If they're not conductive, they cannot be charged. If they cannot be charged, they cannot get collected, right? So it's very dependent on the ash resistivity. So it's basically the same as this earlier one here. Finally, it operates much better when at steady state. Again, it means that you cannot change the operating condition while maintaining a similar efficiency there, right? So what this means is that once we decide to build a ESP, it has to be operating under that condition so that we can achieve a high removal rate for the particles, okay? So since we talked about the removal rate or the removal efficiency, so how do we calculate the removal efficiency? We mentioned that for the cyclones, there are equations to do that, right? So we first calculate the dp50 and then calculate what is the collection efficiency at different sizes. So for the ESP, what we're going to do is we're going to assume that particles have similar sizes, okay? And we're going to choose the most, or basically choose the simplest ESP geometry to calculate its efficiency. And then further to relate this efficiency equation to the actual, to the practical ESP systems. So if we talk about the simplest structure of the ESP, how does it look like? So I already showed that in here, right? The simplest ESP is just composed of two plates, right? It's two parallel plates. It looks basically square shaped, right? And between these two plates, there are basically parallel wires, right? So it can be longer, extending to further downstream. And what happens is that the gas flow are going to go through the gap between the two parallel plates. So let's assume that the gas velocity is u. Okay, so it's in meter per second, right? So the length of the ESP is L, as is shown here. So distance between plates is D. Okay, and also the height of ESP is H, also in meters. Okay, so let's just label here. This is the height. Okay, so if we think about the movement of the particles in this ESP, so you can think that basically these coronal discharge generate ions, right? If we put it under a negative high voltage, what happens is that it's going to generate a lot of electrons. Or basically, or these electrons can get attached onto the oxygen or nitrogen molecules, forming oxygen and nitrogen negative ions, right? So these ions can collide with the particles. There are particles in here, right? So the particles that's on the left of the wires are going to collide onto the left plate, right? Because of the electrostatic force. While the particles on the right of the wires are going to collect onto the right plate, right? So let's assume that this migration velocity of the particle is W in meter per second, okay? So this is the migration velocity. So how do we calculate this migration velocity? So again, based on drag force, right? Particles are going to move in relative to the flow speed in terms of the perpendicular to the flow direction. So what we need to do is just QE. QE is the electrostatic charge, electrostatic force on the particles, equal to FD, drag force, 3 pi mu dp divided by c multiplied by W. Okay, so you see that this W is really dependent on the particle size. So the larger the particle size, the smaller the migration velocity, right? The smaller the particle size, the larger the migration velocity. So this is the something about the migration velocity. So we will talk about that later regarding the operation of the ESP. Okay, so what we need to do right now for the simplest condition is assume that the migration velocity is a constant. So this is a constant for all different sizes. Okay, for all sizes. Okay, so with these assumptions, we can start to analyze how does the concentration change when particles pass through this ESP system. Okay, So what we can do is we can choose two different surfaces. Let's say we just choose a very thin or a very narrow slice of the gas. Okay, so let's assume that at this location is x, and as this location is x plus delta x. Okay, so let's see what happens within this thin slice of flue gas. So we can first calculate what is the flux of the particles going in this box here. Okay, so if we consider the flux of particles, we can just do that by multiplying the concentration of the particles at the location x, multiplied by u, multiplied by h, and multiplied by d, right? So h multiplied by d is just the cross-section area of this ESP, right? H multiplied by d. So we can just multiply with the cross-section area with the velocity and the concentration at the x location. So this is the inflow of the particles into this thin slice here. Okay. So what is the outflow? Outflow is going to be Cx plus delta x multiplied by u multiplied by h multiplied by d. Okay, we just need to replace the Cx by Cx plus delta x. Okay. So inflow minus the outflow, that's going to be the amount of particles getting collected at this surface. Right? So this is a mass balance here. So the inflow or the difference between the inflow and outflow is just the amount of particles getting collected onto this thin surface here. Right? How to calculate that deposited particle amount? So that's going to be Cx plus delta x divided by 2, which is the concentration at the middle of the thin slice, multiplied by W, multiplied by delta H, multiplied by delta X, multiplied by H, right? So delta X multiplied by H is just the area on one side of the plate, right? We know that there are two sides, so we'll multiply by 2. And then this W here is migration velocity, which means how fast the particles are moving towards these two plates here. So that's going to be Cx plus delta x divided by 2, W delta x H multiplied by 2. Okay, so this is the mass balance that we can build on this very thin slice here. So you can see later on how we can use the limit, right? The concept of limit to build a differential equation here. So let's make some rearrangement here. Okay, so we can move the delta x to the left-hand side, right? So that's going to be minus Cx plus delta x minus Cx divided by delta x. The UHD is going to be equal to 2WH multiplied by Cx plus delta x divided by 2. Okay, so we just move delta x to the left-hand side, and we have this equation. So now let's take the limit of x minimizing to 0. So we're going to get basically dc dx multiplied by ud equal to 2wc. Okay, so we're making this delta x, basically delta x to 0, and we can get this differential equation here. Right, and further let's rearrange it. Dc dx equal to 2w divided by ud multiplied by c. Okay, so this should be a quite straightforward differential equation to solve, right? So the way we do that is minus dc, or we can just put the minus sign on the right-hand side, right? dc divided by c equal to 2w divided by ud multiplied by dx. So we can have log c divided by c0 equal to minus 2w ud multiplied by x. Okay, so we just integrate on both sides. This is what we get. All right. So we mentioned that this ESP, the simplest ESP, has a length of L, right? So based on this equation, we can calculate what is the concentration at the end of the ESP. So that's going to be log CL divided by C0 equal to minus 2 WL divided by UD. Okay, so basically we can also calculate with the exponential, put the exponential calculation on both sides. We can get exponential, or the left-hand side, that's just going to be CL divided by C0 equal to exponential minus 2 WL divided by UD. Okay, so we can either use this equation or use this equation. So this is not the most simple equation yet. What we can do for this term is further to multiply h both on the numerator and denominator. So then you can find out that the log CL divided by C0 is going to be equal to minus W multiplied by AP divided by Q. Okay, so the reason behind that is, let's look at here. Okay, L multiplied by H is just the area of a single plate, right? On one side, we have 2 in here, so we change that to AP. This is the area of the plate on 2 sides. Plate. Okay, so we use AP here to represent the area of the plates on 2 sides. So on the denominator, we have U multiplied by D multiplied by H. So D is the distance between the 2 plates. H is a height, and then we multiply that by U. That is the flow rate. Okay, it's the flow rate of the gas, right? So we can use this equation to calculate what is the concentration of the particles at the end of the ESP, right? If we know the migration velocity, we know the area of the plate, we know the flow rate, then we can calculate what is the concentration of particles at the end, okay? So you may wonder, well, this is for the simplest ESP. What about the real ESP, okay? So in industrial ESP, we can use the same equation, except that we have some different meanings for each term, okay? So for industrial ESP, we also have the log CL divided by C0 equal to minus WE A divided by Q, okay? So there are some differences here. So WE is called the effective migration velocity. Okay, so we use a term that's more based on the experience of operating the ESP. So this is also in the unit of meter per second. Okay, so our textbook shows an array of these parameters for different particles or different operation of the ESP. A here is the total collecting area of the ESP. Okay, so the collecting area, now you can see how our previous quiz problem play a role here. Okay, so the A here is not the total area of the ESP. It's actually the area that's being used to collect the particles. So for example, if we're talking about this ESP here, then the collecting area should be 2n minus 2 multiplied by h multiplied by L, right? Because we're just using 2n minus 2 plates, or 2n minus 2 sides to collect the particles. And the Q here is still the flow rate. Okay, so with this equation, we can calculate what is the concentration of particles at the end of the ESP, and then we can use this equation to calculate what is the efficiency, because efficiency is just 1 minus this term here. So we will talk more about this equation later on in our next class. Okay, so I think this class will also derive some equation here. I hope you understand how the ESP works, right? Why we have this equation to calculate the efficiency. So let me know if you have any questions. I'll post this lecture online. All right. So have a good day.